afternoon, gentlemen. I'm Sirapop from TNS Caster. Today I will present the topic of resource allocation in SARS A network online normal. This paper is written by Sheng Wu and a research team from Queen Mary University of London and Western University. So we start with the motivation first. In novel wireless communication, they require high throughput, high reliability, and efficient spectrum utilization. As you can see in the topic, there is 4 keywords, which is resource allocation, reconfigurable intelligent surface or RS, the orthogonal multiple access or OMA, and non-orthogonal multiple access or NOMA. So basically, resource allocation means how can we allocate limited resources like frequency, bandwidth, power consumption, or even physical resources. And reconfigurable intelligent surface is a surface that's made by the metamaterials. So in telecommunication, when base station transmits a signal to the UE, there might be the obstacle in between them. So the signal from base station will face that obstacle, and the power of that signal will be attenuated by the obstacle. So to avoid that, we might use RS in order to reflect the signal from the base station to the UE, as you can see in the green figure. So there is another type of the RS, which is simultaneously transmitting and reflecting reconfigurable intelligent surface or star RS. It can be used to both transmit and reflect also. So the user equipment or UE in the back of the star RS surface can still receive the signal that comes from the station. Okay, so the list of keywords is how can we assign the channel to each UE. So that multiple UE can access the same channel. That's called orthogonal multiple access and non-orthogonal multiple access. So the author state the problem to 4 problems. The first one is complexity of resource allocation. There is joint optimization of power allocation, channel assignment, and also beamforming matrix. So this joint optimization is MVP problem. You cannot solve this in real time. And the second problem is channel assignment challenge. So the author have to decide how can they assign the channel into each UE in orthogonal multiple access scheme and non-orthogonal multiple access scheme. So the third one, basically, beamforming matrix has non-convex nature and has high dimensional. So the author have to find the optimal strategy for beamforming optimization. So the fourth problem is the author have to decide efficiency and low complexity algorithm in order to overcome the exhaustive search of the optimization. So this paper has the objective to optimize resource allocation and to maximize system sum rate. Basically, system sum rates can be measured by sum the communication rate in each user. So the author proposed algorithm to solve joint optimization problems. The first one is location-based matching algorithm. So they use location-based matching algorithm in order to match the user in reflection path and transmission path together in our scheme. And for orthogonal multiple access scheme, they use general design algorithm to match the user in reflection path together and transmission path together. In order to optimize power allocation and decoding order, they design geometric programming algorithm and semi-definite programming algorithm to optimize these 2 parameters. In order to optimize beamforming matrix to gain maximized sum rate, they propose convex upper bound approximation algorithm to optimize these metrics. And the last 2 algorithms that's proposed is successive convex approximation and alternating optimization. They use these 2 algorithms to optimize power allocation and time allocation, and also beamforming matrix in all orthogonal multiple access scheme. So they set up the simulation by placing simultaneously transmitting and reflecting configurable intelligent surface in the middle, and the user equipment are placed uh, further away from star RS around 5 meters, and access points or base station are placed further away from star RS around 50 meters, as you can see in the left figure. So the right figure shows the simulation results in terms of system sum rate versus number of total RS elements. So the x-axis is number of total RS elements, and the y-axis is system sum rate. The blue line is star RSA normal network. Red line is star RSA normal network. Yellow line is conventional RSA normal network. The purple line is conventional RSA normal network. As you can see in the same number of total elements of star RS, the star RSA normal network can perform the most system sum rate. And in terms of sum rate versus user location, the x-axis is user location, the y-axis is system throughput or system sum rate. As you can see in the same user location, the blue one is star RSA normal network can perform system sum rate the most. From the simulation results, we can conclude that the star RS normal significantly outperform both star RSA normal network and also the conventional RS in terms of sum rate. And the proposed optimization framework further enhance resource allocation, resource efficiency. Sorry. And the last one is star RSA normal can maximize resource efficiency and also system sum rate. Thank you for your attention. Do you have any questions?